Hello, my name is Vitaly. I'm from the Technical University of Denmark. In this video, we will talk about how to choose the topology of a matching network for preamplifier decoupled magnetic resonance imaging coils to achieve best signal-to-noise ratio. Preamplifier decoupling is a widely accepted technique in the receive coil arrays and is used to avoid undesired detuning of array elements. We have previously published the design equations for all possible 3 and 4 element networks. There is a wide variety of networks to choose from, and there are no clear guidance for which circuit topology to choose for particular implementation for better noise performance. The resistive loss of the network can significantly degrade SNR at the input terminals of the preamplifier. The process of identifying which component of the network is driving SNR degradation and how to minimize this effect so far has largely been based on experience of the coil designer. A diagram of the considered here array element consisting of a coil preamplifier and matching decoupling network is illustrated on this slide. In this setup, the noise figure of the matching network can be reliably estimated using these two approximate and exact equations. Here, Rc is the coil resistance, R11 is the real part of the input impedance of the matching network Zi when the preamplifier A is disconnected. The approximation holds for the typical case of using a low input impedance preamplifier, which is pre-matched to 50 ohms. The relationship reveals that the SNR degradation is defined by the ratio between the loss in the components defining R11 and the coil loss. To demonstrate this, let's consider an example. Here we have an oval-shaped coil for carbon imaging in mice at 3 Tesla. The Larmor frequency is around 32 MHz. The impedance of the coil, preamplifier, and matching network output are indicated on this slide. To realize this matching network, the shown two topologies can be used. The values of the matching network components are calculated using the design equations given in this paper. The corresponding coil current or preamplifier decoupling is shown here on the left, and the measured SNR is shown on the right. The ratio of the unloaded Q to loaded Q is also indicated here at the bottom. An experienced coil designer would point at the 3-element matching network as the one having worst SNR. This is indeed what we measure here. Let's use our formula to find out the reason for that. In this table, you can see at the top the resistance values for both networks extracted from simulations, and at the bottom corresponding calculated noise figures. As can be seen from the previous slide, the measured SNR of the 4-element network is higher than the SNR of the 3-element network by 6.6 decibel, which implies noise figure difference of 6.6 decibel, as both setups use the same preamplifier. Simulation predicts a little over 7 dB SNR difference, which is close to measurements. Noise figure estimated by the exact equations is very close to simulated noise figure, with errors below 0.29 decibel or 7%. It is also clear that the last term, Rout divided by Rout minus R22, is negligible. Thus, in this example, approximate formula can be employed. The noise figure equations explain the difference between the SNR of two considered here networks. The inductor L2 contributes significantly to the term R11, whereas the inductors L4 in the 4-element network contributes only to R22, and therefore have small influence on the noise figure. Inductors are typically much more lossy compared to capacitors. Their place in the network should be carefully chosen to avoid significant contribution to R11. The derivation of noise figure equations is based on the property of passive networks that noise figure is inversely proportional to the gain of a two-port network. I encourage you to read the details in the paper. A formula to predict the noise figure of low-loss matching networks is derived for the case when the reactance of the preamplifier compensates the output reactance of the matching network. It serves for the analysis of competing network topologies to identify solutions leading to higher signal-to-noise ratio. The formula was used to predict noise figure at 32 MHz with reasonable accuracy and is confirmed by simulations and experiments. If you have more questions, you're welcome to contact me by email.